This is episode 3 of Geometry Explorations, in which we look at triangle area a little bit. This series was motivated when I posted something to say how little I liked geometry when I was in high school, and yet I grew up to be a geometer. So let me show you one of my favorite types of geometry facts. It's because it connects things that you don't expect to be connected. It's very unexpected. Let's start with 2 points, A and B, and postulate 1 says, given those 2 points, that a straight line can be drawn connecting them. We'll say more about straight lines next time, but we know what that means. Now, choose a point not on the line, and we're not exploring the parallel postulate, at least not yet, so let's create triangle ABC. And here's the challenge. I want you to find all of the points so that if you build a triangle AB with that other point, it has the same area as our triangle ABC. If you're curious, this would be a good time to pause and give it a try. Find all of their points X such that the area of triangle ABX is the same as the area of triangle ABC. So the key here is that A and B are fixed. So we could choose an X below AB so that ABX is the mirror image of ABC. If I choose this X and I draw this triangle, it's like I've mirrored it around AB. Clearly, those triangles have the same area. So that's one. Are there any others? To help us understand this, consider what is the area of a triangle. We know the formula is the area is base times height over 2. And in this image, AB, the length of AB, let's call that the base, and the perpendicular distance to C is the height. So what if we just choose another point that has that same height and draw that triangle? It must have the same area because it's a half base times height. Or this one. In fact, any one that has the height h, any point along this line. This is familiar. This is the parallel postulate. We started with the concept of area, and we ended up with a line through C that is parallel to the line AB. I find this mind-blowing. For completeness, we also have our point X below, the one that was straight down, and so we also have the parallel line through that point. So this problem gave us 2 parallel lines to AB, one through C, and one to the reflection of C through the line AB. It's amazing to me that the statement of this problem had nothing to do with parallel lines or angles. We just fixed AB, we chose some random point C not on AB, we considered the triangle ABC, and then we asked, give us the rest of the points X so that the area of ABX is the same as the area of ABC. We compared areas, and we ended up with parallel lines. And it turns out that the area of a triangle being proportional to base times height is equivalent to the parallel postulate. In fact, we've just shown that. And that leads us to our next exciting moment where we say, but what happens in worlds where there are no parallel lines? In fact, what do lines mean in those worlds? So next time we'll take a closer look at straight lines.